Well, let's review C sub B for a second. We'll get into some new topics. Review C sub B. So what is C sub B? What's it all about? What's it help us with? Well, it has something to do with beams. What's it help us with on beams? That's right, second or third zone, right? And it only helps us with one of our Snell charts, right? One of our Snell charts. C sub B helps us out here. It increases our capacity. But then we're capped by the M sub P, right? Okay. So how many different C sub B's are there? 3. 3 different C sub B's in this class. Okay. There's one of them that you use, the most common one. It's the one you learned in undergrad. It had the 12, and everything is used as a everything that you use is a positive number. It looks something like that. It's the most common C sub B. Right? Okay. Use the maximum moments, the moment at the quarter point, the half point, and the three-quarter point. You plug into this value, and the more curvy something is, the higher the number should be. Okay, and that's the most common C sub B, and you apply it between the braces. Okay, and then we have 2 other C sub B's. And what are they for? They're special cases. Therefore, when you have a beam that's braced on the ends and then braced on the top flange. Right? And in one case we have gravity loads and the loads are coming down. And in the other case we have wind loads and the loads are coming up. Right? Remember that? And why do we need special C sub B's for these cases? Probably the most important thing that you could have learned from the lecture last time. So why do we need different C sub B's for this situation?
Because they're acting the moments change the whole entire how it's going to end and everything. It's completely different.
Yes, that's true. The moments here are going to change.
Brace completely different because of that.
Yeah, I mean, I think you said the keyword brace. You said that really a lot of people might think about this structure and say that it is braced. And they might say that L sub B is 0. Or something very small. Right? And what did we learn the real value for L sub B was? Entire length. Okay, that's number 1. But we do get some support and some help from these braces at the top. Some. It'd be conservative to assume that they're not there. But then if you did that, then every single building would be in danger by calculation of collapsing, and they don't collapse. Not all the time. Why? Well, it's because you do get some benefit from these braces up here. So how do you take that benefit into account? Well, that's how they've come up with C sub B for case 2. These braces do provide us some support at the top, and that now helps us with this C sub B. Notice this C sub B starts at about 3 and then goes down. Okay? It can go up, but it starts at a nominal higher value. You get more benefit from these situations. The C sub B, in effect, helps you deal with these situations. helps you give you a little bit more capacity. And remember, the C sub B is not exactly right. The solution that's closer to being more correct is the differential equation. It just happens to be nasty and long. Okay, so you use this, and this is a one-liner if you understand how to use the rules, but you don't have to deal with the differential equation. Now, then we have this situation where the load is up. And this now becomes extremely dangerous because this bottom flange is now in compression. And what do we know? We had in our review last time, we had a situation where we had a moment that looked something like that. Nope, take that back. A moment that looks something like that. And we talked about having a brace at the top. And we said, is that an effective brace? And everyone said no. It wasn't. That's what we learned the day before, right? Or the lecture before. It wasn't an effective brace. Is that okay? Good. That's true. Now, in this situation that we're talking about, in the past we were talking about simply supported beams, and that was great. Now we have situations where we have continuous beams, where it's not a constant moment diagram anymore. If it was a constant moment diagram, then everything I told you before is correct. L sub B is still L, okay? C sub B is 1. You use the diagram. You use the Snell charts. In a circumstance where we don't have a constant moment, though, or in the circumstance we showed in case 3, where we have some areas of compression and some areas of tension in the bottom flange, now we don't have a constant C sub B anymore. So how do we take that into account? Well, that's what this does. And this actually has 2 separate versions of a C sub B for case 3 that you calculate, depending on what the end moment situations are. And these are not hard, these are just about following directions. Okay? What's important in this class and in your life is to understand why we do these things, okay, and what's going on, so you know when the rules are being broken and when they're not, and why we need this and when we don't. So this circumstance where we might not have, our moment diagram may not be constant, our moment diagram may look something, well, I drew it wrong. Moment diagram may look something like this, right, because we're talking about uplift. This idea where all of this bottom flange are being in compression and these are not. These are actually helping it, and these are actually in compression, and structural engineers, for whatever reason, are not very good at doing 5 pages of differential equations to solve the answer to this. Okay? And so instead, this helps them get to an approximate answer that's correct. Does that make sense? So understanding why is just as important as understanding how. I think I've said that before, and I'll keep saying it, I guess. Awesome. There's the C sub B's. They're done. Knock that out. Cool. Now we get to see some more stuff we've seen before. Before I forget, I promised you last time that I would show you the page that is the secret to the other Snell charts. And if you turn on the 14th edition to page 16.1-16, if you just read over here, it'll tell you this. This tells you what your gamma, your different gammas are, and these are actually the much more useful. These are for webs. No, take that back. These are. Let's see. These are for webs. In here. And these are for your flanges. Okay. No worries, we're going to come up to a nice summary table in my notes that shows what are the important factors. Okay, it's coming. Okay, but just warning you, and the reason why, remember, we're building up to something where we're actually going to have 3 different Snell charts, and then we'll add a 4th. Okay, Snell chart. So it's always good to understand where you're going. Okay, cool. Now we're going to talk about beam design, and this is totally review. You should know all this stuff. And this is for rolled sections. Okay, we're not going to spend a lot of time talking about this at all. But just in case you haven't seen these before, we're going to be using the Z tables. The Z tables, which looks something like this, where they give us all the key points on the Snell chart. It gives us M sub P, M sub R, L sub P, L sub R, and this bending factor is actually the slope of the line. The slope of the line in zone 2. Okay? Other cool things on here, it gives you I sub X, and it actually gives you phi VNX, which we'll talk about today. Snell chart, or this is the Z table. Very useful, very cool. And these are great if you have a C sub B factor of 1, right? This tells us what all the values are for C sub B of 1. Here's the C sub B table over here that's somewhat useful, and then there's always the equation, right? Case 1, case 2, and case 3. Most common one to use is case 1. Then we have the Snell charts, which are table 310 on page 396. Well, it used to be 396. Now it's a little larger, now it's 399. And what this has done is, this is pretty cool. This is moment diagram over here on the y-axis. This is L sub B. Oh, you can't see it. This is L sub B down here on the x-axis. And this shows you your flat part, your linear part, and as you're going, you can see different parts. What they've really done here is they've printed all of the Snell charts. All of the Snell charts for all the different members. Huge poster. Massive poster. And they've gone back and cut those up into individual pieces and pasted them. So these are all little sheets from the huge poster of the Snell chart. And why it's cool is it's useful to be able to compare different things. So you can come in at L sub B and a phi M sub P, and you know that everything above that is safe. What does a dashed line remember? Does anyone remember what it means? It means there's a lighter member. There's a lighter member that provides that same capacity. So if you ever get to a point of the Snell chart, you keep going up until you hit a solid line, and that happens to be the lightest member that has that capacity for that section. Remember, the Snell charts are derived for a C sub B of what? 1. C sub B of 1. Snell charts are actually derived also for an Fy of 50 KSI. So what do you do in Z tables are as well? What do you do if I give you a 36 KSI? If you go back into your notes, there's actually tables, there's actually equations I gave you that you could use to calculate L sub P, L sub R, all those things. Okay? There's equations you could use to get your own Snell chart version of the Snell chart if you needed to. Okay, that's cool. That's cool. Several snapshots are shown of the moment capacity versus unbraced length for all rolled sections. L sub P's are closed dots. L sub R's are open dots. Dashed lines means a lighter section exists that provides more capacity. Everything's derived for an Fy of 50 KSI and C sub B of 1. Now, I think I start working problems now, and we don't need to talk about each one of these problems in general, but they're good if you're not comfortable, if you don't remember, if it's been a long time since you've done C sub B's and M sub P's and L sub B's and all that stuff like that, or this is a good thing to look up and review. Now, please recall that there are situations where we have a C sub B that can actually knock us above what our phi M sub P is, right? And in that situation, we can never go above phi M sub P. And I think the last example does a good job of that. I think this is one, and I'm not going to go through the numbers. You should go through the numbers yourself. I think I have a problem here where I put a load on it. I've got a moment diagram and a shear diagram. I calculate what the C sub B value is. I get 1.32. Gotta recall that C sub B can increase our moment capacity up to phi m sub P. This said in another way, I show lateral torsional buckling times C sub B, it has to be less than or equal to phi m sub P. Basically, I can increase this capacity, increase this Snell chart, but I am capped by phi m sub P. And then I show this for design purposes. What's often done is you divide everything by C sub B. Makes things easier to do. Okay? And now we can just look up this capacity in the Snell chart. We can always, and then there's two ways to look at it. You can either look at that, say, phi m sub P divided by C sub B, or you could look at that value times C sub B if that's what you wanted to do. I look this up in the Snell chart, find the most efficient size, find this point, continue to go up until we hit a solid line. So I do this, I find a W30 by 173 works, I look at the phi m sub P, and I go ahead and I check myself. I said, hey, this is the modified equation. This is the one where I divided by C sub B on both sides. Remember this? Okay, if this is cloudy to you, you don't understand what I'm doing, you better go back and look for yourself. Okay, I go and I look this is the value I'm designing for, this is the value I looked up in the Snell chart. I compared it to my phi m sub P divided by C sub B, and I'm okay. So the section should work. Then I said it's always a good idea to check things the proper way as well, or another way. I'll go ahead, if this doesn't make sense to you what I'm doing, you can always do the process like this. You can take your design moment of 1800 kip feet, take your beam capacity of 30 foot in length, and multiply by 1.32. That's my C sub B factor. I get 2138 kip feet, which is greater than 1800. That's good. That's making me feel good. 1800 is what my design moment is. My C sub B times my lateral torsional buckling gets me a value that's greater than that number. Again, that's making me feel good. I always have to compare this number, though, to C sub B. I'm sorry, to phi m sub P, and that's what I do right here. 2280 kip feet, 2138. So if we did this graphically, this is what the original Snell chart was. This is the value of 1620 at 30 feet. I multiplied by my C sub B factor. That's the 1.32. That's what knocked me up. Knocked it up by 30%. It just so happens I was still underneath my phi m sub P, 2280 versus 2138. Does that make sense? If I, for whatever reasons, would have been here and tried to knock my value up to here, that wouldn't be allowed. That wouldn't be allowed. I would have capped myself here. Why? Because that's what C sub B factor does. C sub B factor takes into account that I have a nonlinear moment diagram on my cross-section. Because I have a nonlinear moment diagram, the derived equations for lateral torsional buckling are very conservative. And I can up those capacities. I can do so up until the point where I reach phi m sub P, but I can never go higher than that. Okay, so I think we've covered this 2 to 3 different ways, 2 to 3 different days. Hopefully it's all making sense now. This is where we actually start to see the numbers. If it doesn't make sense to you when you do the numbers, when you work through these problems yourself, you need to come see me. 2 other things briefly. Capacity of steel beams and shear is a bit of a joke. I say, hey, for rectangular sections, our shear diagram is fairly nonlinear. For these sections that look something like this, that they're not nearly as wide, I get a much more uniform shear diagram, and this is approximately, I can ignore this, I can ignore this, and I can ignore the nonlinearity here, and I approximate it as a constant value over something like V over A. Okay, and that works fine for things that are not wide, okay, and that are tall. Okay, that's a decent assumption. So this is what they end up using inside the steel manual for I-shaped sections, an equation that looks something like this. And this equation is going to come back later on. This C sub V. Does everyone see this C sub V? The C sub V is going to come back and haunt us later on. You're going to hate this value later on. Okay? We're fortunate right now, though, because I say practically, and you can just mark out the word practically. All rolled sections all W shapes in the manual, all rolled sections have compact webs. What? What does that mean? I ask you that question. What does that mean? Compact. We've mentioned that word before. We're in zone 1 in the web slenderness snail chart. Remember, we have 3 snail charts. One for lateral torsional buckling, one for slender flanges. Is that a problem for rolled sections? Only for about 6 sections, right? It's the actual reduction in capacity is like about 5% or so, right? So I'd say no, it's not a big deal for rolled sections. Okay, so now let's talk about the 3rd snail chart, the slender web. Is that a problem for rolled sections? I'm telling you the answer is no, it's not. I'm telling you, for every one of those slender web snail charts, remember slender web snail charts? This is gamma MN again. I'm sorry, this is phi MN and this is gamma at the bottom. Remember that? Yeah? We're saying that we're always here. That means that C sub V is always 1. Okay? So it's just Fy times area web. Don't worry, when we get to plate girders, that won't be 1 anymore. Okay? Okay. So the cool thing is everything's in the Z table. All these shear strengths are reported in the Z table. They're there. You just look it up. It's easy. No calc needed on shear. Let's talk about deflection limits. Okay, because steel has an extremely high modulus, designers are able to reduce a member's weight by making it slender. That's what the name of the game is. We always ask you to find the lightest section, don't we? Because that's cheapest. Well, in theory, it's cheapest. It's not always. Okay? There's a lot of things that go into cost, right? A lot of things that go into cost about type of construction, how easy it is to construct something, things like that. How if something's very complicated, if you have a different size beam everywhere, oh my gosh, it's like a puzzle putting it together, right? Very hard. But oftentimes we like to, at least in academic problems, calculate the lightest. Okay? And it's kind of the mantra of steel designers everywhere. Light, light, light. Right? So due to this slenderness, steel members can have excessive deflection or vibrations when used as beam members. And vibrations is the key here. Okay? Deflections are important. They are. They're very important, and they can cause issues. But oftentimes you have things like drop ceilings, like we have in this classroom. So you can't even see the steel members above them. So you don't even really know or care how much the deflections are. The lights don't really change. Things don't really change that much. Sometimes you can get cracking in partition walls, but oftentimes if you look very closely, you can see airspace between the ceiling and the wall. So you can get deflections, and who cares? It's not going to cause any problems. But vibrations are important, extremely important. Okay? How you observe a building, how you feel in a building is important. And if a member is bouncy and beams are bouncy as you walk around, it's going to make people feel uncomfortable. It's going to make them worry about the capacity of the structure. And actually, again, if we were to do things exactly, we would do dynamic analysis on structures. Dynamic analysis. We would find out what the natural frequency is of the structure. We would compare that natural frequency to the typical natural frequency of loading. Okay? There's some good papers out there on how to do that. It's not that hard about what the natural frequency of a human walking is, or natural frequency of a cart being pushed down a hallway is. When actually they have numbers on what the natural frequency of what a gym is, like a gym, like riding a bike, and exercise rooms and things like that are. And you want your structure to not be at that same natural frequency. Because if it is, then as it's loaded at that natural frequency, it will become excited. Okay? And what are typical deflections that aren't that big of a deal get magnified. And that's what dynamic loading is. That's what dynamics is about. Okay? Understanding that. Now, we don't want to do that because that's a whole semester of class that you would have to expect people that commonly just have undergraduate degrees to have. to be able to design a structure. Okay? And we don't want people to have to work 3 or 4 pages of problems just to see what the deflections are. So what they did instead is they said, I'm just not going to let it deflect very much. I'm just going to make it stiff. And if you make it stiff, you often move the natural frequency away from these natural frequencies that commonly cause problems. Okay? That's why that's in there. Again, it's really important in this class to understand why just as much, if not more, than how. Okay? Okay. So excess deflections have caused cracking in plaster, made occupants feel uncomfortable. That's from vibrations. Okay? It's from vibrations. Because of this, some deflection limits from service loads, I've underlined service loads twice. What are service loads? What's that mean? It means live load. Doesn't mean dead load. Dead load, actually putting dead load on your structure actually helps you. If you've worked on something that's very flexible and you put a lot of dead load on it, it actually holds it in place. When you go and you start to load it again, it doesn't bounce as much. If you're ever driving on a truck, I think someone just the other day was telling me that their 1-ton truck drove so much better when it was loaded with 5,000 pounds of rock in the back, as opposed to when it was just driving by itself. Okay, when it was loaded down, the bumps didn't really affect it as much. It drove smoother actually than when it was unloaded. It hit the bumps and it bounced all around. Okay. Okay. So we care and we check for deflections and movements on service loads. That means live loads. Okay? Live load deflection limits. That means cars, that's people, things like that. It's not dead load deflection limits. It's really important. You also use you don't use a load factor when you calculate deflection limits. No load factors. Okay? No load factors involved. But typical limits, live load deflection limits for if you have a plaster ceiling, people think things like L over 360 or L over 240. These are common numbers. On a roof, you want no ponding to happen, right? In a bridge, you often have a much more stringent live load deflection limit. You've heard that, surely in some point in your career, you've heard about armies marching across the bridge and shaking them apart, right? You always tell armies not to march in step as they go across a bridge. Okay, especially as bridges get longer and you go away from beam type systems, you go to cable stay type systems and truss type systems. Your natural frequency gets much higher. Okay, and it happens to correlate commonly with step on a march. Okay, it'll shake the bridge apart. Okay. So they'll tell armies to not march in step on a bridge, right? Okay, and they'll also make bridge beams have much more stringent live load deflection limits. Again, please realize all of these are made up. All of these are not real. Only in the case of causing cracking in plaster ceilings or in your walls are only time these are real deflection limits. They're often just substitutes for doing a much more complicated analysis. Okay? Okay. Hey, man. Blew through that. Okay. More stuff. Yeah, stiffeners aren't going to help you at all for vibrations. Not at all. Stiffeners are local. Stiffeners help local problems. Okay, vibration is a global problem. The only way you can change vibration issues is to change the natural frequency. And to change the natural frequency, you change the stiffness and you change the span length. And stiffness can be modulus. Good luck with that with steel. and I. Okay, so you can change E or I, or you can change span length, or you can change the rate of loading. Good luck with that. I mean, tell people to walk differently. Okay, shuffle. Everyone shuffle down the hall, right? Like, you know, goes to that song, you know, shuffling. Okay, so does that answer your question, Jacob? Put another column in.
When you were saying stiffness, I thought you were saying like stiffness, not like increasing the I.
Yeah. So does it make more sense now?
Yeah.
That when we have vibration problems, it's a global problem, and you got to increase I, or some other trick, decrease fan length, something like that. Hey, this is something I came up with because I think it's just a nice summary of how to design in general with one Snell chart, only using one Snell chart. Okay, this idea that flexible design of long girders, that's when L sub B is greater than L sub P. This is the same stuff we've said before. This is just saying it in a different way. If we're in these zones, okay, if we're in one of these zones, I said basically when you have a structure with complicated moment diagram and different braces, this is the brace, right? Brace and a brace. That we're going to have different span lengths, different C sub B's, and different moments, right? So I said you're going to find the maximum moment for each length between the braces. We'll call these segments, okay? Find the maximum moment for A, B, and C. You're going to draw the moment diagram for each of the segments and find the C sub B for each section. So you got moment, maximum moment. You got C sub B for each section. You have L sub B. You know what this is for each section, right? Use C sub B, the maximum moment combinations, to find a beam section that controls for each of the sections or each of the L sub B's. Basically, you'll do that trick we talked about before. Your moment capacity is your lateral torsion buckling capacity times C sub B, and that has to be less than phi m sub P. And you're going to repeat this for each segment. So you're going to have to, almost in a sense, do 3 different designs. 3 different designs. And then you're going to pick the one section that satisfies all 3. Check the maximum shear for the chosen section over the entire length. Find the maximum live load deflection over the entire length and check the limits. Hey, live load deflection, this is unfactored. Don't forget, unfactored. That's just a nice summary, I think, of what we talked about before. Okay. So now let's talk about shear. Interphase shear. Oh, and I forgot some stuff that I meant to bring with me, but it's okay. I'll have it next time. We're gonna start to talk about what happens when you design composite girders. Composite girders mean when you have a beam, and then on top of that beam you put something else, like a slab, like a concrete slab on top of a steel girder. Okay, and you've seen this or not, believe it or not, when you did strength of materials, because you talked about nailing 2 different pieces of wood together, and how big are the nails and how close do they have to be. So you've worked these problems. It's just too bad they lied to you in that class. Okay? I wish that wasn't the case, but I can understand why they did. Because everyone through time has been lying to you in that class. But that's okay. We'll learn the full story here. So if I have a simple supported beam with a distributed load on it, and I'm talking about element A, talking about this element. So it's not in the dead center where shear is 0. It's not in the end where moment is low. I'm talking about an intermediate element. Okay? So this element's in here and in here, in this zone. And if I take this element out and I look at the loads on it, I have moments on both sides, and I have shears on both sides. And believe it or not, if I compare the right-hand side to the left, this is real important. If I compare the right-hand side to the left, I actually have more shear on the left side. Why? Well, that's what the shear diagram told me, didn't it? That's what the shear diagram told me. I'm comparing this to this. There's more shear on the left-hand side. And if I compare the left-hand moment to the right-hand moment, I actually have more moment on the right side. Does everyone see that? That's just comparing this point to this point. Same thing. Okay? So, that's interesting. That's interesting. That's important to understand. So, if I drew the stresses on the cross sections, the stresses from bending, the stresses over here would be higher than the stresses on the left. Sigma 2 would be higher than sigma 1. You with me? Why? Because the moment's higher, isn't it? You okay with this? Now, if I take a cut at A, and I take a cut at B, let's just talk about A first. A cut, a magical cut. And I look at everything above it, above that cut, and I compare, I've just told you, and you all agreed with me, at least you shook your head yes, that the stress on the right was larger than the stress on the left. Yes. So what's that mean about resultants? The resultant from this stress has to be higher on the right than it does the left, doesn't it? Has to be. So that means there has to be some internal stress to make up the difference. I'll say that again. You all agreed with me that the moment the bending stress was larger on the right than it was the left. And then I took a cut and only looked at the stuff at the top. And because the stress is higher, then that means this resultant, or the area underneath this stress diagram, is larger than the area underneath this stress diagram. That means that for that cut to be in equilibrium, that there has to be stress on the face of the cross-section. This is called interface shear. As we take cuts at different depths, we find our tau diagram, our shear diagram. Looks like this. Whoa! That's what I told you to memorize. And remember, we just forgot why. We forgot that, if we think about this force, this differential force, it'll be the maximum at the middle because that's where the maximum differential will be. Think about that. Right? That's where the maximum differential has to be. Cross-sectional area is the same. Load over cross-sectional area is stress. That means the stress is the highest. At the very, 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 very top, we take our cut right up here. There's almost no differential. Because there's almost no differential, the interface shear is zero, or almost zero. You with me? And it varies non-linearly over the depth of the cross-section. Are you okay with that? Okay, pretending to be. Thank you. So we use this relationship to design members in shear, and we also use this same idea with a built-up section. Same concept. And you've seen this before. You've worked problems previously where you had two pieces of wood, you had a nail, and there was a beam and bending. And you wanted to know how big the nail needed to be and how close it needed to be spaced. Usually they gave you one, the size of the nail, and you picked out how close the spacing had to be. And we're going to work this exact same problem in this class. It's going to be exactly the same. We talk about interface shear. The nail is responsible for holding the two sections together or transferring the interface shear. This. Transferring the interface shear between the top and the bottom piece. As always, this is not the whole story. This analysis assumes no slippage and no yielding at the interface. It assumes no slippage and no yielding. So we're going to talk about, you know what, I'm going to stop right there.